For centuries, humanity perceived the vast expanse of space as a silent void. This notion, however, is a misconception. The universe is a symphony of sounds, a cosmic orchestra playing out a grand and mysterious composition. Recent discoveries by NASA have shattered the myth of a silent cosmos, revealing that even black holes, those enigmatic cosmic behemoths, have a voice. We often think of sound as something we hear through the air, but sound can travel through any medium that can transmit vibrations. In the near-perfect vacuum of space, sound as we know it cannot travel. However, the universe is not completely empty. Vast clouds of gas and plasma permeate galaxies and galaxy clusters, providing a medium for sound waves to propagate. The detection of these cosmic sounds is not just an auditory curiosity, it provides scientists with a new tool to study the universe, complementing traditional observational methods based on light and other forms of electromagnetic radiation. In 2003, astronomers using NASA's Chandra X-ray Observatory made an astounding discovery. This observatory, which has been a cornerstone in the field of X-ray astronomy, has allowed scientists to peer into the most energetic and enigmatic regions of the universe. The Chandra X-ray Observatory, named after the Nobel Prize-winning astrophysicist Subrahmanyan Chandrasekhar, has been orbiting Earth since its launch in 1999, providing invaluable data on cosmic phenomena. They detected sound waves emanating from a supermassive black hole residing at the heart of the Perseus galaxy cluster, located a staggering 250 million light-years away from Earth. This galaxy cluster is one of the most massive objects in the universe, containing thousands of galaxies, vast amounts of hot gas, and dark matter. The supermassive black hole at its center is a powerhouse of energy, influencing its surroundings in profound ways. This marked the first time acoustic phenomena had been observed from such a distant source, providing concrete evidence that space is far from silent. The sound waves detected were not audible to the human ear, as they were in the form of pressure waves traveling through the hot gas in the cluster. These waves have a frequency so low that it would take about 10 million years for one oscillation to occur, making them the deepest note ever detected in the universe. The black hole at the center of the Perseus galaxy cluster is a true cosmic monster, containing the mass of hundreds of millions of suns. Its gravitational pull is so strong that not even light can escape from it, making it an object of intense study and fascination. The immense gravity of the black hole affects the motion of galaxies within the cluster and the distribution of hot gas, creating a dynamic and complex environment. As matter falls into the black hole, it heats up and emits intense radiation, including X-rays. This process, known as accretion, is one of the most efficient ways to convert matter into energy. The X-rays emitted by the hot gas near the black hole provide crucial information about the conditions and processes occurring in these extreme environments. This radiation interacts with the surrounding gas, creating pressure waves that propagate outward, much like ripples in a pond. These pressure waves, or sound waves, carry energy away from the black hole and can influence the temperature and density of the gas in the cluster. By studying these waves, astronomers can learn about the properties of the gas and the mechanisms driving the dynamics of the cluster. The discovery of these sound waves sent ripples of excitement through the scientific community, opening up new avenues for understanding the behavior of black holes and the dynamics of galaxy clusters. This finding has implications for our understanding of how energy is transported in the universe and how black holes can influence their surroundings on a large scale. It also highlights the importance of continued observations and advancements in technology to uncover the mysteries of the cosmos. The sound waves emanating from the black hole in the Perseus galaxy cluster, while groundbreaking in their discovery, were initially far too low for human ears to perceive. These waves, detected by NASA's Chandra X-ray Observatory, were a significant find, revealing the dynamic and often violent nature of black holes. However, the challenge lay in making these waves accessible to us. The frequencies were so low that they were beyond the range of human hearing, essentially making them silent to our ears. These deep cosmic bass notes resonated at a frequency of a B-flat, but a mind-boggling 57 octaves below middle C. To put this into perspective, middle C on a piano has a frequency of about 261.6 Hz. The sound waves from the black hole, however, had a frequency of approximately 10 million years per cycle. This is so low that it would take millions of years for one wave to complete a single oscillation. Such a frequency is far beyond the range of human hearing, which typically spans from 20 Hz to 20,000 Hz. To make these sounds audible and comprehensible to the human ear, NASA scientists employed a technique known as sonification. This innovative process involves converting data into sound, allowing us to hear the otherwise inaudible. Sonification has been used in various fields, from medical imaging to financial data analysis, but applying it to astronomical data opens up a new realm of possibilities. By translating the data into sound, scientists can gain new insights and make the information more accessible to the public. Sonification is the process of converting data into sound. In the context of the Perseus galaxy cluster, this meant taking the incredibly low-frequency sound waves detected by Chandra and transforming them into something we can hear. The process involves mapping various characteristics of the sound waves, such as frequency and amplitude, to audible sound parameters. This allows the data to be represented in a way that is both informative and engaging. In this case, NASA scientists mapped the frequency, amplitude, and other characteristics of the sound waves detected by Chandra to audible sound parameters, such as pitch, loudness, and timbre. This meticulous process required careful calibration to ensure that the resulting sounds accurately represented the original data. By adjusting these parameters, scientists were able to create a sound that not only conveyed the information, but also evoked the awe-inspiring nature of the cosmic phenomena. By scaling up the frequency of the black hole's sound waves by a factor of quadrillions, they were able to bring them within the range of human hearing. This dramatic increase in frequency allowed the once inaudible waves to be transformed into a sound that we could perceive. The process of scaling up the frequency involved complex mathematical transformations, ensuring that the integrity of the original data was maintained while making it accessible to our ears. The result? An eerie, haunting wail that sent shivers down the spines of those who first heard it. This sound, unlike anything heard before, provided a visceral connection to the distant and mysterious black hole. It was a reminder of the vast and often unsettling nature of the universe, a sound that seemed to echo the very fabric of space-time itself. The haunting quality of the sound captured the imagination of both scientists and the public, sparking curiosity and wonder. This was not a musical composition in the traditional sense, but rather a raw, visceral representation of the universe's hidden symphony. The sonification of the black hole's sound waves offered a new way to experience the cosmos, turning abstract data into an auditory experience. It highlighted the power of sound as a tool for scientific discovery and public engagement, demonstrating that even the most distant and enigmatic phenomena can be brought closer to our understanding through innovative techniques. Sound, unlike light, requires a medium to travel. While light can traverse the vast emptiness of space, sound needs a medium such as air, water, or solid materials to propagate. This fundamental difference between light and sound is why we can see distant stars and galaxies but cannot hear the cacophony of the cosmos. It cannot propagate through the vacuum of space, where particles are too sparsely distributed to transmit sound waves. In the vacuum, there are simply not enough particles to carry the vibrations that we perceive as sound. This is why space is often described as eerily silent, despite the numerous energetic events occurring within it. However, the Perseus galaxy cluster, like many other galaxy clusters, is permeated by a vast reservoir of hot, dense gas. This gas fills the space between galaxies, creating a medium through which sound waves can travel. The presence of this gas transforms the Perseus cluster into a unique environment where sound can exist. This gas, primarily composed of ionized hydrogen and helium, acts as a medium for sound waves to travel, much like how sound travels through water or air. The ionization of these elements means that they have lost or gained electrons, making them electrically charged and highly energetic. This state of matter, known as plasma, is common in the universe and plays a crucial role in various astrophysical processes. The gas in the Perseus cluster is not uniformly distributed. Instead, it forms a complex web of structures with varying densities and temperatures. These variations are influenced by the gravitational forces of the galaxies within the cluster and the activity of the central black hole. It forms a complex dynamic structure with regions of higher and lower density. These density variations create a rich tapestry of interactions as sound waves travel through the gas. The waves can be amplified, dampened, or scattered, depending on the local conditions of the gas. The sound waves from the black hole interact with these density variations, creating echoes and reverberations that provide clues about the distribution of matter within the cluster. These interactions are akin to how sound waves on Earth can reflect off walls and objects, giving us information about our surroundings. By studying the propagation of sound waves through the cluster, astronomers can map the distribution of this gas, which is invisible to traditional telescopes. This mapping is achieved through sophisticated techniques that analyze the frequency, amplitude, and phase of the sound waves as they travel through the gas. This, in turn, provides insights into the cluster's formation and evolution, as well as the influence of the black hole on its surroundings. Understanding these processes helps scientists piece together the history of the universe and the forces that shape it. The Perseus galaxy cluster, with its unique medium for sound, offers a fascinating glimpse into the dynamic and interconnected nature of cosmic structures.